So here's our questions. Number one, what step is not included in the scientific method? So I'm hoping most people remember the scientific method because that's, of course, a point of emphasis you're going to have on both the first and final exams. Which one of these is not part of the scientific method? You said B. Okay. I thought you said something else. I had to read them. Well, hey, I can't hear well. Okay. Now, what are the steps to the scientific method that you have to reproduce on the exams? Step one, what is it? Observe something interesting. What was step two? Okay, develop a hypothesis with three things. It needs to explain why the observation occurred. It needs to be based on scientific ideas. And it needs to make testable predictions. What's step three? Okay, devise and do a test of prediction of hypothesis. And then finally, step four is a little different than the others. What is step four? It's determining the outcome of the test. In computers, we'd call it an if-then statement. If the hypothesis passes, P-A-S-S-E-S, you probably wouldn't know that's passes except for the fact that I said the word. What do you do if the hypothesis passes the test? Then go back to step three. And test a different way or a different prediction. So I'm just going to put differently. Else, if it fails, then what do? Go back to step two. Because now you have more information so you can make a better hypothesis based on that new information. Okay, so that was all about question one. Going to question two. What makes things move? Forces do. So that was C, force. Number three, what is a vector? It has to have two things, the magnitude and the direction. Magnitude and size are the same thing. I think the person who made this, no, they said direction and magnitude. Why was B not the correct answer? Okay, speed is a scalar. It doesn't have direction, it just has magnitude. Velocity is a vector. It has direction and magnitude. And if it said, what is an example of a vector, velocity would have been a correct answer. But speed and velocity, of course, is not going to be a correct answer. Finally, what is average speed? It's which one?
The rate at which position is changing?
That is correct. The rate at which the position is changing. It's the delta x, so change in position, over delta t, which is what makes it the rate. Now, if you have a problem with any of these questions, they were written by your classmates, find who wrote it and argue with them. Obviously, if you think the answer's wrong, you can argue with me, but if the question wasn't a good question, that's your classmates to take it up with. Of course, I do go through and choose the ones I think are best, so you could also take it up with me. Okay, any questions about the quiz? No? Okay. Moving on to material, falling objects. When objects fall, we talked about last class period, they have an acceleration that's due to gravity that is 9.80 meters per second squared. Our textbook, to make calculations simple so we can do a lot of things in our head, says, 9.8 is reasonably close to 10. So how about if, for learning, we just use 10 for the acceleration of gravity so we can do the calculations in our head real easily. So if you drop a ball, what happens to the acceleration of that ball, assuming no air resistance as it falls? What happens to the acceleration?
It'll constantly increase.
It'll be constant. It'll remain constant. Here we're going to say that approximately 10 meters per second squared. The acceleration isn't going to go up, isn't going to go down. It's just going to stay constant, assuming there's no air. If there's air, then that's going to make it constantly, well, not constantly, it's going to make it decrease until it reaches zero, as we talked about when Colby asked the question. So we're going to have a constant acceleration as it goes down. But acceleration, we didn't have that on our quiz, so what is acceleration? Okay. It's the rate of change in velocity, so delta v over delta t. So that means if I know that it has a constant acceleration, I know how fast the speed is changing. The velocity speed depends if it's vector or scalar. So I can take this and solve it for the velocity. Well, I'll put change in, I put an equal sign, and that's wrong. That's bad math. Change in velocity is equal to acceleration multiplied by change in time. Okay, that's on top of things. Can't write on top of things. Bad form, right? Right down here. Change in velocity or change in speed is acceleration multiplied by change in time. What does change in always mean? It's blank minus blank. Which minus which? Final minus initial. So this change in velocity means the final velocity minus the initial velocity is equal to acceleration times, and change in time is final time minus initial time. To make our lives easy, we always just say the initial time is going to be 0. That is, I'm going to drop the ball at time equals 0. Start my timer when I drop it, just like you did in the lab, right? And since I dropped it, what was the initial speed? How fast was it going when I was holding it in my hand? 0. So it's going to start with initial speed. So I usually keep v initial in here in my equation. But for this case, v initial is going to be 0 plus our acceleration, which is 10 meters per second squared, multiplied by t final. Now this makes it real easy to determine how fast the ball will be traveling after 1 second, 2 seconds, 3 seconds. For instance, after 2 seconds, I would just say the velocity, the speed, after 2 seconds is the acceleration, 10 meters per second squared, multiplied by my time of 2 seconds. 2 times 10 is 20. If you look at the units, if I put the numbers in that I just said, the speed is equal to 0 plus 10 meters per second squared times 2 seconds. Notice seconds divided by seconds squared. That's, anything. If I did well, let's put it in numbers because a lot of students are just more comfortable with numbers. If I have 5 divided by 5 squared, what's that equal to? Just 1 over 5, because 1 5 on top cancel with 1 5 on bottom, leaving 1 over 5. Now these are S's instead of 5s. Looks similar. It's the same thing. This second cancels with one of those, and I'm left with 20 meters per second. So the units work out. Yeah, it's units of speed now. They'd better work out. If you get speed with the wrong units, like speed with units of time, you know you made a mistake somewhere. So we can calculate the speed the ball is going to have after each second. That's not very hard, is it? Is it? No? Well, okay, I'm going to move on. No one's agreeing or disagreeing there, which usually means they disagree. What about the distance that it travels? How could we calculate the distance? Notice it has the distances marked here. How do we calculate those? We worked out the equation that said that delta x is equal to, and I'm going to put the fullest form possible, x initial plus v initial multiplied by time plus 1/2 a times squared. That's the most complete form you can have. But if I say, well, I'm going to start it at 0 position, then I can make life easier and make x initial 0. And if I'm going to drop it, I can make it easier and say the initial speed is 0. And then we get exactly what Andrew, I think it was Andrew who said it, wasn't it? Yeah. Okay. So I just have 1/2 my acceleration multiplied by time squared. What was the acceleration? We're making the approximation to make it simple that it's 10 meters per second squared multiplied by the time squared. Or in other words, 5 meters per second squared multiplied by time squared. So after 1 second, how far has it traveled?
Or 5 meters.
5 meters, right, because 1 squared is 1. After 2 seconds, how far?
10.
More than 10. Remember, it's times squared. So I have 2 times 2 is 4 times 5. So that's 20 meters. And so you can see the numbers out here. Here's the calculation for 2 seconds, 20 meters. For 1 second, 5 meters. When we were doing this in lab, some people tend to think, oh, it might be a second. A second, it travels 5 meters, not just 1 meter. But how long was the time that we worked out in class Monday for dropping a ball 1 meter? It was how much? It was something around, I think, 0.45 or 0.47 seconds. And once again, I'll actually do the calculation again. I can find that by taking this equation and saying, I want to find the time for a specific distance. So I'm going to take the delta x is equal to 1/2 at squared and solve it for time. So since time squared is multiplied by a over 2, I'm going to divide both sides by a over 2. Remember, divide is the same as invert and multiply, so the left side becomes 2 delta x over a is equal to t squared. The last step, how do you go from t squared to t? Mathematically, you take the square root. So I simply square root both sides to find my time. Technically, when you square root, there are 2 answers, a positive one and a negative one. But we can be pretty sure that it's not going to be a negative time to drop 1 meter. So we're just going to take the positive one, so time is equal to square root of 2 multiplied by the distance it's going to travel divided by the acceleration. And so if I bring up the old calculator, oh come on. If I bring up the old calculator, just like I did last time, I have 2 times 1, because it's 1 meter, divided by, and I'm going to use the correct acceleration now, 9.8 meters per second squared, and square root it. And you see 0.4517, whatever. We didn't have that kind of precision, so 0.452 seconds would have been the best possible answer for us to use when we did this. Okay, this is going to make it blink, but it'll come back. Maybe it'll make it blink. There we go. So that's how we can find the time that it takes for it to fall. Here is a graph that shows the position as a function of time. Basically what's been done here is the answer, that delta x, has been calculated for a bunch of very small increments for time and then plotted there. And you can see that's not a straight line. The distance the ball has traveled is not following a straight line. The graphs that we've been focusing on, right, the ones I talked about in lab, that we looked at in lab, those all had a straight line. This one's not. If you look at acceleration versus time, you have constant acceleration, You look at distance versus time, you have constant acceleration. It shows a curve. And in fact, there's a name for this. It's a parabolic curve because it's proportional to time squared. And not yet. This is a ridiculously dumb question. If I throw a ball down, will it hit the ground before or after the time it would have taken to drop one? Before, right? Ridiculously dumb question. It's going faster, so it's going to take less time. But if I throw it down, once it leaves my hand, I'm no longer affecting it. So what's the acceleration going to be once it leaves my hand? It'll be the acceleration of gravity, the 9.8 meters per second squared, or what we're approximating right now is 10. Once it leaves my hand, it'll keep speeding up because of that acceleration. So I can calculate its speed at any time if I threw it using this relation. Anybody know what this means? It means initial. That 0 means at the starting. So you could put V sub I or V sub 0. It means the initial time. And most people say V naught. Somehow I was taught to say V aught. Doesn't really matter, I suppose. So the speed is just going to be the initial speed plus the acceleration multiplied by time. And likewise, the distance, since distance by definition is delta x, this equation here is a complete equation the way they show it, the completest equation that includes all of your variables. So those you use if you don't start from rest, right, where you can't just say those initial variables are 0. Life is not so easy as just dropping a ball. I can take a ball and throw it up. Life is more difficult. And so we're going to look at how to work with situations where you throw the ball up. So now once again, really, really stupid question. Remember, not any stupid question. It's just stupid people who ask them. If I throw the ball up, is it going to be in the air longer or shorter than it would have been if I just dropped it? Longer, clearly. Because it's got to go up and then come back down. So we're going to have a longer time. What's the acceleration going to be of this ball once it leaves my hand? It's going to be gravity. It's going to be accelerated downward due to gravity. The entire flight, once it leaves my hand until I catch it again, it's just going to be the acceleration of gravity that's pulling it downward. So here's a picture of a gentleman throwing a ball up, and he's actually a pretty darn strong gentleman to just go like this and throw it up 20 meters. That's a pretty good distance to throw a ball like this. Anyway, so the calculations are done here for the position and time as it goes through. Notice it starts with an upward speed of 20 meters per second. That's just how fast he threw it. And then it shows at 1 second, it's gone up 15 meters. How did they calculate that? They just used the equation we had on the previous page. I went through and changed this to red. I noticed that all but one letter was not red and changed it. I don't know what's... Oh well. Distance is equal to v initial plus 1/2 acceleration multiplied by time. Now when I do this equation, I suddenly am faced with a situation that we haven't really paid attention to. What direction is the velocity at the moment the ball leaves the hand of this gentleman? Up. What direction is the acceleration of gravity by very definition? Down. So they're in opposite directions. So when I put in this equation, I need to decide what direction am I going to use positive numbers for, and what direction am I going to use negative numbers for. What do you suppose the standard is? Treat up as positive. So I'll put an arrow that's up and put a plus sign. That means up is positive. So my speed initial was 20 meters per second. Positive because it was upward. Oops, I forgot to put the time there. Man. It's bad to make mistakes. Plus 1/2. And what will I put for my acceleration? Negative 10 meters per second squared. The 10 because that's the approximation we're making here for simplicity and calculation. The negative because it's down. And then times squared. And so now I can calculate after 1 second, distance at 1 second is equal to 20 meters per second times 1 second plus 1/2 of minus 10 meters per second squared. Well, that did not come out right. So, of course, this first term, 20 meters. Second term, minus 1/2 of minus 10 is minus 5 times 1 squared, which is just 1. So that's how we can calculate the distance. If I go to 2 seconds, I would, of course, have, well, let's just do it. The distance at 2 seconds (20 times 2 is 40). 5 times 2 squared, which is 4, is 20. So that's 20 meters after 2 seconds. And if I go up to 3 seconds, (60 meters minus 3 squared is 9. 9 times 5 is 45. So minus 45 meters equals 15 meters. So you can see that it went 15, 20, and then back to 15. And you look at the numbers here, that's what you see for the heights. So it went up, it stopped, and it came back down. What can you tell me about the velocity as it was going through this process? Its direction and magnitude. What was happening as it was going up? The velocity was what direction? As it's going up, the velocity is up, and we had decided to call up positive. So as it's going up, the velocity is positive, and what's happening to the velocity? Is it getting bigger or smaller? Getting smaller, slowing down. When it's at the very tip top, the velocity is going to be 0. What does 0 velocity mean? It stopped. So it's momentarily stopped at the top, but it comes back down. As it comes down, what direction is the velocity? It's negative, it's down. And is it getting bigger or getting smaller? It's getting bigger. So going up, it was upward, getting smaller. At the top, it was 0. Coming down, it was negative and getting bigger. Now we're going to switch to the acceleration. Remember, acceleration is the rate at which the velocity is changing. So as it was going up, the velocity was upward but getting smaller. So what direction was the velocity changing? In the negative direction. So what does that tell you about the acceleration? It was down. At the tip top, the velocity was 0. What was the acceleration there? Not 0. Think about how I asked the previous question. The change in velocity divided by time is how we get the acceleration. So if the acceleration was 0, how much would the velocity change? It would change by 0. And so the velocity would stay 0. So if the acceleration was 0 at the top, I'd throw the ball up, it would stop, and it would just hover there. But that's not what happens. What happens? It what?
The acceleration turns positive.
No. The ball was going up, it stops, and then what does it do? Then it comes back down. So the velocity was changing from an upward to 0 to downward. What direction was the change then? It was downward. So there was a negative acceleration at the top that made it so it didn't stay at a 0 velocity but came back down. And as it's coming down, the velocity is down and getting bigger. What direction is the velocity changing? Getting bigger. It's going downward. And so the acceleration must be down. So the entire time, the acceleration was downward. And in fact, we've said this previously. What should the acceleration have been the entire time? The acceleration the entire time should have been equal to g. G is the symbol we use to mean the acceleration of gravity, pointing downward. So it was constant. We used the number 10. Remember the true number, 9.80 meters per second squared down. The entire time. Why do I spend time going over this? Because it is extremely common to get velocity and acceleration confused. We all know that we have the gas pedal in the car that we call the accelerator. And because of that, we start getting the two velocity and acceleration confused. And so people often think because the velocity at the top was 0, it must have an acceleration of 0. But that's not true. When you're driving your car, if you have an acceleration of 0, you're just going at a constant speed. But you don't think of it that way because you're pushing down on the gas pedal to keep it at a constant speed. And so that's why you have, I think, a disconnect there. So, important thing out of this is, throughout its entire flight, the acceleration on the ball was constant, g pointing down. So, our first clicker question. What is the ball's acceleration at the top of its path? Uh-oh. I have a typo, don't I? No. Okay. Notice the units here are different than the units for the two below. On the computer screen, it's covering, so I can't see that. Okay, everybody has answered. We had 1, 1, 4, 1, 3, 0. So turn to the people nearest you, person nearest you, whichever it may be. So you guys can discuss among yourselves, you 3, you 2, you 3. And discuss what you answered, why you answered. Okay, let's see how your peers affected your thinking. So answer again, and we'll see how your peer teaching did. Well, the person who said that it had zero acceleration changed. That's good. And the person who said, well, one of the people who said it accelerates upward changed. And at this point, we have a plurality that said the correct answer. Now, all but one person had down. That's good, because the acceleration is indeed downward. What's the difference between answer C and E? Velocity versus acceleration. Answer C is a velocity, whereas answer E is an acceleration. How do I know the difference? Well, I'm a teacher, of course. Because you have the meters per second squared for acceleration. So this one here was wrong just because it had the wrong units. This was wrong because it had both the wrong units and the wrong direction. This was wrong for the wrong direction. And of course, 0 is just plain wrong. And no way of knowing is, well, silly answer. Any questions at all? Is it clear? These kinds of things we don't want students to be confused about. So I showed you a graph previously of what position looks like as a function of time. Here is velocity as a function of time. How would you take this velocity graph and find the acceleration from it? This goes back to Monday. Take the slope. The slope of this is going to be the acceleration. Looking at that graph, is that a positive slope or a negative slope? It's a negative slope, so it's going to have a negative acceleration, downward acceleration. How would you find the distance traveled from this graph? The area under the graph. So I can do this, and I'd say, okay, 0 time, the area is 0. If I come out here at 2 seconds, the area would be the area of that triangle. 1/2 base times height, 1/2 of 20 times 2, 20. And then it's going to start going back towards 0. So if I get out here to 4, I'd have a plus 20 and a minus 20, bringing me back to 0 after 4 seconds. So when it's a negative, when the velocity is negative, then it's the area between the 0 line and where it is there. Let's see. Who sent me a text here? Is it? Okay. I was going to make this announcement. I just got a text message that said, don't tell anyone. So good. I won't tell you guys that. Yeah. Well, I can give you one of the two announcements I was going to give. We have a new person that we've hired for math professor. He has accepted the position, the person who came and interviewed Anthony Bosman. Yeah.
So what math is he teaching?
He won't be arriving for another year. And I'm not sure what he'll be teaching. They'll have to switch the schedules around to match what people are better at. But it's really exciting to me. Okay. Projectile motion. We're going to talk about not just things going up and down, but things traveling a distance. So who's fairly confident they can catch the ball when I throw it to them? Okay, Denford. So I'm going to throw the ball to Denford. Now, first simple question. If I throw the ball to Denford, should I throw it straight at him? If I throw it really hard, that'll work, but what do I need to do if I'm going to throw it at a reasonable pace? I need to throw it up so that, oh, sorry, that was too short. Well, could have thrown it to anybody if I'm going to make a bad throw. Try it again. Better. Not perfect, but better. You could reach it. Okay, so I had to throw it upward, and then what happened to it after it left my hand? Okay, it went up, and then it reached its peak and started coming back down. Once it left my hand, here's a really important thing that a lot of people are confused about. Was I affecting the ball after it left my hand? No. So now we talk about follow through. Like when you throw a baseball, you want to have good follow through after that throw. What's the point of the follow through? It cannot influence where the ball goes. So it's not for where the ball goes after it leaves your hand. It's to make sure that your motion was pure until it left your hand. If you have an abbreviated follow-through, you're probably going to start adjusting before it leaves your hand. And so that's why they talk about the follow-through being important. There also is your own personal safety, right? If you throw a ball and you go like this and just try to stop your arm like that, you're going to damage your shoulder. So there's another reason to talk about the follow-through. But you're not affecting the ball once it leaves your hand. So I wasn't affecting it. I wasn't making it come back down. It was whatever was going on. Now, I didn't have any spin on it. When you said broke. When we talk about it breaking, we're usually talking about the spin changing the motion from what it would be if there was no spin. The without spin is a simple trajectory. The spin makes a big difference. In fact, if you play golf, which I don't, if you play golf, the spin you put on the ball makes it travel quite a bit farther, like 3 times farther than it would if you didn't put any spin on it. Right? So the spin makes a huge difference. And if you've ever watched video Christy Matheson throwing a ball around three pegs that are in a row so it goes and bends around them, you see the spin makes a big difference. For our class, because there's no air that we're considering, spin won't make a difference. So when I threw it, it went up. I wasn't affecting it. What made the ball come back down? Gravity. What direction is the acceleration of gravity? Down. So when I threw the ball, or when you threw it back to me, the acceleration was downward. When we talk about the motion in 2 dimensions, this was 2-dimensional motion, one horizontal and one vertical, we can treat the motion in those 2 directions as completely independent. So I can talk about the motion going horizontally from me to Denford, completely separate from the motion of the ball going up and down. So when I break it up, I have 2 parts of the problem. One part is I threw the ball and it went up and it came back down. The other part is I threw the ball and it traveled horizontally. And of course, the time that it took for the ball to go up and come back down needs to be the same as the time it took for the ball to go from me to Denford, or it's not going to get to him. Like my first one. Right? The time for it to go up and come back down was less than the time that it took to get to Denford. It didn't get to him. But we can treat those two parts as completely separate. And so we break our problems into a horizontal part and a vertical part. Now, this here is a fun question because, well, who didn't like, this is supposed to be, without breaking copyright, Wile E. Coyote. Who didn't like Roadrunner and Wile E. Coyote when they were kids? I always rooted for Wile E. Coyote. I thought it wasn't fair that all of his genius, super genius if you were to believe his personal business card, plans didn't work.
It's all because the Acme company sucks.
I know, Acme, really? He should have gone to somebody else. But I mean, it was Acme. That means it's at the peak. It's best.
Clearly not, because every religion.
Speaking of user error, Colby, you haven't answered yet. Okay, our answers here were 1, 8, and 1. How dare you say Wile E. Coyote would have user error? That's not what happens. When you run off a cliff, you don't just keep going horizontally until you realize, uh-oh, there's nothing underneath me, and fall straight down. That's not the way it happens at all. When do you start falling if you run off a cliff? Immediately. Now, say that you start falling immediately. Does that mean the correct trajectory? Trajectory is what we call the path it takes. Would go like this. You're right, Andrew. It would not do this because when we talked about the ball falling, its speed the instant after I dropped it was just minusculely above 0. And the speed slowly increased, well, slowly at a constant rate. So the downward speed is going to get faster and faster and faster, while the horizontal, what's the acceleration in the horizontal direction? How much of gravity is horizontal? Gravity's what direction? Down. Down is perpendicular horizontal, so none of the gravity is horizontal. So the horizontal motion is just going to go at constant speed. So it's going to go at constant speed horizontally, but speeding up going down. And so what that trajectory actually looks like is shown here. And that's what Andrew did with his hand. I know none of you except for me could see it because he's in the furthest back of everyone. If you look at these pictures, notice, is it accelerating horizontally? We had a lot of questions like this. The answer is no. What was your reasoning?
Because there's nothing pushing him forward.
Okay, that is a correct and true reason. But from this picture alone, we can answer no, it's not accelerating because the space between each one of those 0.1 second intervals is the same. So that means the distance divided by time is the same, constant horizontal speed. But the vertical speed, if you look down, is that accelerating? Yes, because each one is a farther distance, which means the average speed was picking up. This here is talking about how we break a vector into components. Vectors having directions, and we break it into the horizontal part and the vertical part. And we actually do this using trigonometry. If we have an angle here, then we can use the definitions of sine, cosine, and tangent, which I am not going to go over today. What's the difference in those three trajectories? It's the velocity they went off with. One of them went off really slowly. So, okay, that was too slow. So it just barely goes over the edge. One went off much faster, so it goes out farther. Now, in terms of time, which one hits the ground first? They all hit on the same flash of your strobe, right? This is supposed to be the strobe pictures like we had real before. They all land at the same time. How's that possible?
Constant
Yeah, they have the constant acceleration down. They started with the same downward velocity of 0. So this brings up the classic question. If I have a bullet, this hand, and I have a revolver in this hand, I put the revolver perfectly level, and I pull the trigger and drop the bullet at the same time, which bullet hits the ground first?
Oh. Yes.
Okay. The answer for general physics is both, or general physics, principles of physics as well, is they hit the ground at the same time. Because we assume no air resistance. And we assume a perfectly flat Earth. Right? If the Earth is not perfectly flat, then the bullet that went out horizontal, if you went out like a mile away, that wouldn't be horizontal anymore for that same direction. And so the curvature of the Earth would make it stay in the air a little longer. And air resistance on that bullet will also affect the time in the air. But if the Earth was perfectly flat and there's no air resistance, both assumptions we make for this class, then they would hit at the same time because they both had 0 vertical velocity initially, both have the acceleration of gravity the same downward. They're going to fall exactly the same rate. So if I am out shooting a gun, which I don't do, I believe everybody should have a right to a gun, but I'm still scared that I would misuse one. But if I'm out shooting a gun, and let's say that I wanted to shoot the window out of that house across the way, how do I need to shoot? I need to shoot upward because even though the bullet goes really fast, it's going to fall. So when people are actually aiming guns, they have sights. And those sights don't point parallel to the barrel. They adjust the sights so that if your barrel's like this, the sight's going horizontal. So that it will go up and come back down to hit where you're aiming. And so you have to adjust those sights for how far away the object is, for how fast the bullet speed is. There's a lot of things to go into how you set those sights. Because otherwise you can't aim. And so if you have a little laser beam on your gun that points the direction the barrel is, that will tell you where you're going to hit if it's really close. If it's far away, you have to adjust that laser so it's not parallel with the barrel. Okay, we're out of time. Have a great hump day.